Alright, so today we are going to talk about quantum numbers. So I guess we'll start off by saying what they are. So our quantum numbers, there's four we're going to talk about. The first is labeled with an N, and that is just your principal quantum number. The second is labeled with like a cursive L looking guy, and that's your angular momentum. Next is a M sub L, and that is your magnetic quantum number. And then the last is your M sub S, which is your spin, or it's sometimes called spin magnetic. And that should be a bunch of gibberish to you right now, and hopefully we'll get it figured out in a second. Alright, so in order to do quantum numbers, you kind of have to understand electron configurations. And so that's why I have you do electron configurations beforehand. Alright? So just a quick review. If I want to do the electron configuration of carbon, right, there's two ways I can do it. Right? I can do 1s2, 2s2, 2p2, or the way you need to do it until you get really good at these to do quantum numbers is you need to do the box diagrams. So remember, 1s has one line, 2s has one line, and 2p is going to have three lines. And then I filled up my s, so I have an up and a down. I filled up my 2s, so I have an up and a down. But then carbon is only 2 into the p, so it's an up and an up. Remember, you have to put one in each before you can double them up. Alright, so here's the electron configuration for carbon. If we want to talk about the quantum numbers now, this is an electron configuration for the entire atom, for all the electrons within carbon. Quantum numbers are talking about one specific electron. So for our purposes, let's focus on this electron right here. I just chose one at random. Alright, so remember the three quantum numbers again are N, L, M sub L, and M sub S. Alright. N is the easiest darn one you'll ever find. Your N, it's just the number in front of the letter. It's your principal quantum number. It's basically your energy level. So your energy level here is 2 because you're in the 2p. So our N is 2. That's about as simple as it gets, right? Okay. Your L is pretty easy as well. There's an equation for it, and it can get more complicated, but really, it just remember it this way: S equals 0, P equals 1, and so on, right? D equals 2, and F equals 3. So if you were in the 3s, your quantum numbers here would be 3, 0. If you were in the 5p, you would be 5, 1. So our P, or our L here, our angular momentum, is, since we're in the P, and P equals 1, is 1. Just like that. So we're in the 2p, so it's 2, 1. Alright. Now, M sub L is Again, there's an easier way and a little more complicated way. The way you should think of it is, it is going to be greater than or equal to negative L and less than or equal to L. Alright, so let that sink in for a second. So if you think about your L shape, it's going to be greater than or equal to negative L, and less than or equal to positive L. So what that means is if you have S, your only possibility is 0. If you have P, you can be -1, 0, or +1. If you have a D, you can be -2, -1, 0, 1, or 2. How I do it, how I think about it, is just when I go to label them out, you make the middle one 0, and then you just kind of count backwards and forward. So this one would be -1, this one would be 1. Right. If we had something like a D, like let's say we have 4D, where they have 5 lines, something like that, then same thing. That's a 0, then that's a 1, that's a -1, that's a 2, that's a -2, and you're good to go. So in this case, our M sub L is -1. If it was this electron, it would be a 0. If it's this electron, it would be a +1. Now, lastly, our spin, our M sub S, you have two options. It can either be a +1/2, or it can be a -1/2. It's kind of almost arbitrary what you give it. The way, and this will make more sense in a minute, but the way I do it is I just say if it's up, it's positive. If it's down, it's negative. It's really arbitrary, and you'll understand why in a second. So this electron has the quantum numbers 2, because it's in the 2p, 1, because it's a p, and p's are 1, -1, because it's in the -1 subshell, and +1/2, because I arbitrarily called it +1/2, because it's up. If we were to consider fluorine, the electron configuration of fluorine, the only difference here, right, I'll just kind of box it here. Okay, this is for carbon, whereas if we want to compare it to fluorine, our 2p for fluorine would look like this. Okay, first got to fill them all up facing upwards, and then come back down and face them back down again. So now, if we considered this one for carbon, if we want to consider this one for fluorine, the quantum numbers are going to be almost exactly the same, right? They're going to, it's in 2, it's in P, it's in -1, so it's going to be 2, 1, -1. The only difference is this one is pointing downwards. So if this was our carbon example, right, our fluorine example would just be 2, 1, -1, and -1/2. And the reason that is because the Pauli exclusion principle, a guy named Pauli, was a scientist, obviously, said that no two electrons can have the same quantum numbers. So really how it works is whichever spin the one you're given has, it could be a positive, it could be a negative, yours has to have the opposite spin to make sure that they don't ever have the same quantum numbers. Alright, so let's do a couple examples real quick. We'll start with nitrogen. This is a worksheet that you'll get in my class. That says write the electron configurations and the quantum numbers of the last placed electron. So, nitrogen. If you know where nitrogen is on the periodic table, that will help a little bit. If you don't, you probably need to get a periodic table to do this. Okay, so nitrogen is the 7th element on the periodic table. So we are going to need to use 7 lines. Again, let's do box diagram because it'll make life easier. So it is smack dab in the middle of 2p. So we're going to have 1s, we're going to have 2s, and we're going to have 2p. It's going to fill up our 1s, it's going to fill up our 2s, and it's 3 in to our 2p. So there's the electron configuration. Is actually the box diagram. Right, these often have boxes around them, but I don't care too much to bother with that. And then now we write the quantum numbers for the last placed electron. So I just do this out of habit real quick. So we have N, we have L, we have M sub L, and M sub S. So 2p, that's right off the bat real easy. That means 2, 1. We are in the 1, right? The 1 subshell. And our spin, I'm going to call it positive 1/2 just because it's pointing upwards. Alright, one more. Chlorine is smack dab in the middle, actually it's at the end, of the 3p. So we have 1s, 2s, 2p, 3s, and 3p. So kind of make some lines here to make it a little easier to tell them apart. Just throw these together real quick. Even though you know you're filling all these p's up, it's just a good habit to go all ups and then all downs. Right, and now here's the tricky part. You're the second to last electron. So up, 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 down, down. One more would be argon, but we're not. So this is the electron we're talking about. So our quantum numbers were in 3p, so it's 3, 1. If we want to do this, it's 0, -1, 1. So we're in the 0. And again, it's arbitrary, but because it's pointing down, I will call it -1/2. And that is how you do quantum numbers.